Well, first I want to say thank you for joining me today. I'm really excited to talk with you about developing a data ingestion pipeline that gives you real-time access to your data without having to deploy a single server or EC2 instance. Let's go ahead and jump in. We'll talk a little bit about who I am. My name's Steve Abraham. I'm an AWS Solutions Architect. In a previous life, I was the lead SQL Server DBA for T-Mobile for a number of years. I then went into independent consulting. I did a lot of work actually for the US State Department to help them build their communications platform, and a lot of work for Hasbro. Most recently, before coming to AWS, I owned my own software company in Tampa, Florida, and I joined AWS last year. So what we're going to talk about today is, like I said, a data ingestion pipeline. We're going to collect 1 billion data points over the course of a given month. We're going to collect it from varied clients. That means mobile devices, PCs, et cetera. We want near real-time access to that data. And we need high performance and high availability, something you would normally get by building out EC2 instances with elastic load balancer and auto-scaling groups. And we are also looking for low cost and low maintenance. And then later we're going to be joined by Brian Philippou, the Director of Business Intelligence from Zillow, who's going to talk about his particular implementation of this. So there are two end states that we're going to take a look at today. The first one is the end state of Amazon Redshift. And you can see on the left we have a number of different sources of data, and they're going to send their data through the API gateway. API gateway is going to leverage Lambda, and then that Lambda function is going to funnel that data into a Kinesis stream. Kinesis then is going to use Lambda functions again to read that data off of there and push it into S3. When that data hits S3, then it's going to put a record into SQSQ that says that that file exists. And then we'll talk about something that I like to call a looping Lambda function that will load that data in real time into Redshift. The other architecture we're going to look at is very similar. It's the same general ingestion pattern, but instead of dealing with S3 and SQS, we're going to be loading that data directly into Aurora, our new relational database server. And I'm going to talk a little bit about the difference between Redshift and Aurora and when it would be appropriate to use each. So let's go ahead and get started with the API gateway. So in the diagram here, we're going to kind of build out from left to right. And so we have the clients, they're all writing through to the API gateway. What is the API gateway? It allows you to create REST-based endpoints, and it's fully managed. There are no servers, there's no pre-provisioning of servers, you don't need to scale anything, that happens for you. It enables rapid development, and I'm really excited for Brian to share about his particular story about just how rapidly they were able to develop using this. And there are flexible security controls in place. So you can use IAM, you can use a pre-shared key, a number of different options. There are 4 different integration types. One is Lambda, which we'll talk about today. Another is to proxy to AWS services. It is possible to just use the API gateway as a proxy into Kinesis or into SQS or many other Amazon services directly. You can proxy to an existing service. Maybe you have a SOAP-based service right now, and you want to create REST-based endpoints, but you don't want to rewrite your code. You don't want to stand up new servers. This allows you to very quickly and easily set that up. And we also provide mocks. So if you have a software development team that needs to integrate with your API, but you don't have the time yet, you haven't gotten around to developing the core of the functions in that API, you can use our mocks so they can continue to do their development against it. You can also, with the API gateway, deploy to stages. And you can define what those stages are, but for example, dev, test, production, but those are flexible. You can create as many and name them whatever you like. We support cross-origin resource sharing, which allows for API gateway to work nicely with an S3 and CloudFront combination, maybe a third-party library like AngularJS to allow you to host websites that don't require a single EC2 instance that are instantly distributed across the globe without managing a server farm at all. And something that I think is particularly great about the API gateway is that when you define your API, you can export an SDK for Android, iOS, or JavaScript for your particular API. You don't have to write that. It comes right out of the box for you. The cost for API gateway is $3.50 per million calls. Data in, as with most Amazon services, is free. The data transfer out is between 5 to 9 cents per gigabyte. In our particular scenario, we're not pulling data out, we're just pushing data in. So there is no fee there. And in this particular scenario, for 1 billion calls, we're looking at $3,500. AWS Lambda. So we have our producers on the left. They're funneling into the gateway. When they are received in the gateway, we've attached a Lambda function to those gateway calls, so that in this case, it's a post. And so when this post comes through to our gateway, it invokes this Lambda function. Lambda is a fully managed serverless compute platform. It's event-driven, but there are a couple of different models, and we'll talk about that here in a minute. The platform that you get for your function, so it's important to note that Lambda allows you to write a function and focus on the code. You don't have to worry about the server and the services that run on that server, but it still runs on a server. And so the platform, the context in which it runs, is Amazon Linux. Currently, the supported languages are Node.js and Java, and for those of you that went to the keynote, you probably also noticed that we picked up Python today, which is a welcome addition. You can configure the memory for your Lambda functions from 128 megabytes up to 1.5 gigabytes, and then there's a corresponding CPU allocation that goes along with that, but you just control that one dial with that one number. And then there's a timeout, which until today was 60 seconds, but also announced today it is now 5 minutes. So the way that Lambda gets invoked, there's the direct invocation model. This would apply to the Amazon API gateway or custom code. You can hook right into the Lambda API and invoke Lambda functions directly yourself. And the way that works is the application sends the request into Lambda. It goes through an execution role, which grants permissions to execute the code, and then your Lambda function is executed. There's then the Lambda pull model, and this is applied to Kinesis and DynamoDB streams. And what this looks like is you have, in this case, what we're seeing here is there's a Kinesis stream, and as the data is going in there, Lambda will pull that data source, in this case Kinesis, and then when it detects that there are records in there, then it will pull those records into the Lambda function and allow you to do things like maybe ETL on those records that you've pulled in so that you can handle that immediately. The push model is complementary to S3, SNS, Cognito, and Echo. And what this is that this is really in response to an event. So with S3, for example, when a file is uploaded into an S3 bucket, then that Lambda function gets executed in response to that event. And it passes along metadata like the bucket name, the key name, et cetera, so that you can respond to that as that data shows up. So AWS Lambda and the API gateway, they can work well together. And if you're looking for something that's very fast and easy to deploy, it's automatically scaling. And I can't emphasize this enough that it's 100% utilized and managed. That means that you don't have EC2 instances to log into. You don't have to patch them. You don't have to share SSH keys. You just write the code and deploy the code, and it runs for you. As far as the 100% utilization, I mean, even if you're really great at running a load balancer and an auto-scaling group, you're always going to have some buffer at the top that you're not using. With these two models, then you only pay for exactly what you use. Now, if you do have an existing infrastructure that runs on EC2, and you already have a code base there, and you do achieve high utilization, maybe somewhere north of 90%, then it may make sense to just leverage that existing infrastructure. But if you're looking to create something out of the gate, then these are a great alternative too. So Lambda, it's 20 cents for the first million, or per million requests. The first million are on the house. For our particular scenario of 1 billion requests, we're looking at about $200. And then for the gigabyte second, so I talked earlier about allocating the memory to a function. And so a gigabyte second would be, you take the sum total of all of the seconds, and we break it down to 100 millisecond increments. We sum that up for the month, and we multiply that by the amount of memory that you've allocated to that function, and that's your gigabyte seconds. And so that is very inexpensive. In this case, it's $12.35 for this particular design. But like I said earlier, we could also potentially just proxy directly into Kinesis, which would eliminate this cost altogether. Today, I'd like to just show you a number of different ways that you can do this and give you the Lego pieces, so to speak, so that you can make up your mind about what works best for you. But in this particular scenario, that's what we're looking at. Amazon Kinesis. So again, producers on the left, API Gateway and Lambda, taking that and packaging it up and pushing it into a Kinesis stream. Kinesis is a fully managed data aggregator that can handle terabytes of data per hour. And the way that it's designed is you have a stream, and then the stream is comprised of different shards. When data comes into that stream on a put, then before you get that 200 request back from the service, that data has already been replicated across 3 different facilities. So there's a high degree of data durability when you write to Kinesis. We, until today, had a 24-hour retention period. That retention period is now, I believe it's 7 days. And then the shards are how you add additional capacity. So a single shard will support 1,000 put requests per second and 1 megabyte worth of throughput. And then, of course, 2 megabytes worth of read. And you can think of each of these shards as an individual thread. And I'll explain what that means here in a little bit. That'll make more sense in just a second. So traditionally, a Kinesis application, you have these producer applications on the left, they write to the stream, and then that data is in the stream, and the consumer applications read from that stream. And the consumer applications in here run on EC2. Well, with Lambda, we can get rid of those consumer applications, and we can put a Lambda function on the stream. Now, when I said earlier that you can think of a shard as a single thread, in this particular scenario, we have 5 shards, and they're all executing the same code, but they're executing independently of one another. So in this case, we have effectively 5 threads all reading simultaneously from that shard from that stream on each of their own dedicated shards. For shard management, you can split a shard so that you can add additional capacity to your stream. You can merge shards if you find that you're not utilizing them and bring it back down to reduce cost. And then you can also, if you want to automate this, you can use the Amazon Kinesis scaling utility. This was a tool that was developed by one of my colleagues and is currently available on GitHub. So, Amazon Kinesis with the API gateway. You can, if you need to have a REST-based API, you can put the API gateway in front of it. And this is usually the case if you have maybe a third party you're working with or somebody else where they have a specific requirement of what that API needs to look like. If you are working internally and you have control over the code that's accessing Kinesis, then you can write directly to Kinesis using the Kinesis API. It's the least expensive. So you'll see that right here, the cost for Kinesis in this particular scenario, to size this out, it's 1.5 pennies per shard hour. So a shard is about $11.16 a month. We're taking our billion requests divided by 31 days, 86,400 seconds. We're averaging about 373 requests per second. We're going to go ahead and over-provision a little bit so that we can support up to 3,000 per second. And our total cost for that stream is $33.48 for the month. So incredibly inexpensive. It doesn't even make sense to run something else on another instance when you have something this inexpensive. Now the put payloads, anything that's less than 25 kilobytes in size counts as one put payload. In our particular scenario, for 1 billion put requests, it's going to cost us about $14 a month. So our total cost for Kinesis is $47.48. It's really hard to beat. Amazon S3 and SQS. So, we still have the producers, they run through the gateway, they hit the stream. Now these Lambda functions that are attached to the stream, what they're doing is they're iterating through the set of records that have been provided to them, and they're combining them into a single stream, gzipping them, and putting them into an S3 bucket. When they hit that S3 bucket, like I said, there's a Lambda function that detects that, and it takes the name and it puts it into an SQS queue. The Amazon S3 simple storage service is secure. You can encrypt your data in flight using HTTPS. You can encrypt at rest using either our provided Amazon S3 key, you can provide your own encryption key, or you can leverage the Amazon Key Management Service, KMS. It's durable. It's been designed for 11 nines of durability, and it's scalable. We routinely handle millions of requests per second and currently store trillions of objects in S3. The key management service manages encryption keys for you. No matter how strong your encryption algorithm is, if you don't manage your keys, those keys fall into the wrong hands. It doesn't matter what kind of encryption algorithm you use because they can just use those keys to unlock your secrets. So the key management service will keep those managed for you. They allow you to encrypt and decrypt data directly without having to keep the key on local instances or machines. and it directly integrates with S3, RDS, Redshift, and a number of other services, but these are the ones that are most pertinent to our talk today. There's also, if you want to do it with AWS Lambda, you can access it using the API, and we actually have an example of that I'll show during the demo portion of this presentation. So when you're working with S3, it's important, the name that you pick for your files is important, because when the files come in, if they're named 1, 2, 3, 4, 5 in sequential like that, you can create a hotspot. So what's recommended is that you create a more randomized, at least prefix to those names. In our particular scenario, and the code that I'll show you later, we're actually using a GUID for the whole thing because the name itself doesn't really matter to us. It's being logged in SQS. We're just processing that data anyway. Something that's important to note, too, is that you're ingesting all of this data, right? That data is not always necessary to have all of the time. So we have in S3 a lifecycle policy. And the lifecycle policy allows you to say, after this many days, I would like to either delete these objects, or I would like to move these objects to Amazon Glacier. And Glacier you can think of as something like a tape drive in the cloud. It's designed for data that you don't need on a regular basis. Maybe it's financial records or something that you need to keep for auditing purposes, but you're not really likely going to access that data anytime soon. It's very cost efficient at 0.7 of a penny per gigabyte, and it's secure and durable, much like S3. The Amazon Simple Queue service is simple, easy to set up, as the name would imply. It's secure. You encrypt your data using HTTPS and flight. It's durable. Before you get that response back, it's already been copied to multiple data centers and servers. And then it also automatically scales. It's one of the easiest services to set up. It only takes a few seconds. Pricing for S3, it varies based on tier, the volume of data you have. It varies based on the region. You do pay for put requests and get requests, but for our particular use case here, for 1 billion requests, we're talking $3.87. Okay? Amazon SQS pricing is 50 cents for 1 million requests. The first 1 million are free, and in our particular scenario, based on how many requests we plan to make, we'll be making less than 1 million per month, and so there will be no cost to us for using SQS. Amazon Redshift. So now that we've got the data in S3 and we've got those file names stored in SQS, we have this looping Lambda function that is going to go to SQS. It's going to grab X number of file names, and then it's going to process those and load those into Redshift, and then it will continue to loop from there. Amazon Redshift itself is our fully managed petabyte scale data warehouse. It's very fast. We leverage columnar storage and data compression. It's scalable. You can scale up from one node up to a number of nodes, depending in different types of nodes, and you can do that dynamically. You're not set with just the data warehouse size that you pick initially. It's fault tolerant. The data is replicated across multiple nodes and backed up to S3. And it's very familiar to use. You can connect using ODBC and JDBC, and it uses SQL to query the database. There's nothing unfamiliar about that. The general architecture of Redshift is there's a leader node, which is what your applications communicate with, which receives the queries and figures out what the query plan is going to be, and then it distributes that node across compute nodes. Those compute nodes are then split up into what are known as slices. And so if you look at a compute node, you have a different slice for every virtual CPU you have. So the virtual CPU and a slice of memory comprises one slice. So that workload is distributed across that, and that's one of the ways that we get such incredible performance out of Redshift. So loading this data into Redshift, how are we going to do that? We're going to use the copy command, and the copy command will give a list. It will use a manifest file that has a list of files that need to be processed, and then it will allow Redshift to parallelize that load. You don't need to spin up multiple threads and send all kinds of data in. In fact, it's better to have a single thread that issues a single copy command sequentially with a copy command in it. And then all of the files that are specified in that manifest, they're all part of a single transaction. If one of those files does not load for some reason, the whole transaction is rolled back. You can encrypt credentials in your source code using KMS, and we'll see an example of that in our code later. Redshift and the copy command supports various file types, including delimited, fixed width, JSON, and Avro. And we also support compression, gzip and lzop. We're actually using gzip for the files in our particular scenario here. Micro batch loading is the process of loading lots of very small files. We'd like to have the number of files that we're loading at a time equal to a multiple of the slices or virtual cores in that Redshift cluster. We can define the compression type for each of the columns we're importing ahead of time in the table so we can make sure that we have the right one picked. If possible, it's good to load the data in key sort order. And then we have the SSD node types, the DC1 instance types, that also have really fast throughput that will help with speeding up your Redshift loads. Our infinite loop, the way we create this, is we create an Amazon Kinesis stream with one shard because we want to do things serially here. We want to do it on one thread. We're going to attach a Lambda function to that Kinesis stream, and then we're going to and then within that function, the first portion of it is going to execute this whole copy command, and it's going to load this data, a batch of data, into Redshift. And when that piece is done, inside the same function, it's going to put just a dummy record back into that stream that it's attached to. What will that do? That will trigger that function to be fired again. And so it will continue to run in an infinite loop. What happens if there's a failure? Kinesis with the pull model, whenever you're using the pull model with Kinesis, it will retry that record so long as it's there. So in Kinesis's case, 24 hours before it times out. If you do have a workload where you need to run multiple threads, you can apply the same pattern and simply use multiple shards on your stream. So walking through it, Lambda is going to create a manifest file, which is a text file with a list of files in S3 that it got out of SQS. It will put that manifest into S3. It will call the copy command on the Redshift cluster. Redshift will then load the data directly from S3 into Redshift. Amazon Redshift, like I said earlier, it's easy to spin up, spin down. I have one customer that they only need to do data processing at the end of the month, and they feel more comfortable with Redshift than using something like EMR. And so they have a Redshift cluster, they load a bunch of data in it, they run some reports, they just shut it down. They don't pay for it while it's off. The next month, they start it back up and pick up right where they left off. In our case, we're looking at a 2 terabyte data warehouse just to get started because we can scale up later. There's no reason to over provision. And for our cost, we're going to go with a reserved instance capacity. We're looking at about $365 a month. Amazon Aurora. So similar design here. The difference is that our Lambda functions, instead of writing files out to S3, they're going to directly load the data straight into Aurora. Aurora is our fully managed relational database. It's based on MySQL 5.6. In fact, your applications will not know the difference between Aurora and MySQL 5.6 when they run, because it's wire compatible. We use the InnoDB storage engine. And one of the things that I think is particularly interesting about Aurora is that we're able to achieve up to 5 times better performance than MySQL. And when I say that, I don't mean that an individual query will execute 5 times faster. What I mean is that you can handle 5 times the load. In this case, we have a white paper that details how we were able to achieve over 500,000 selects per second and 100,000 updates per second. Aurora also can leverage multi-AZ so that you have high availability. If one of your instances needs to be patched, it will automatically fail over. Your application won't know the difference. You don't have to do anything to manage that. It's all automatic. And then another thing that I think sets Aurora apart from a lot of other engines is before your command finishes, when you're inserting or updating data into an Aurora table, that data has been replicated 6 ways across 3 different availability zones, which gives it a very high rate of durability. So now the question is, do I use Aurora or do I use Redshift? So Redshift is a data warehouse, and data warehouses are specifically designed for handling enormous volumes of data and have relatively few queries performed on them in a given time period. In fact, there's a limit of 50 concurrent queries that can be executed against Redshift. But if you have a lot of data, up to a petabyte of data, Redshift is a great place to put that. Aurora, on the other hand, is designed for OLTP workloads. So that's a lot of fast transactions, hundreds, thousands, millions of transactions at a time. There is a limit of 64 terabytes on that, but that's still quite generous. And like I said earlier, 500,000 selects or 100,000 updates per second. So for Aurora, there are two different price components there. There's the compute component. In our case, we're looking at a DBR3X large. Taking the reserved instance option, we're looking at about $235 a month. For storage, storage is a little bit different than the other RDS options out there. Frequently, when you run a database on AWS, it's very I/O intensive, right? So you will use provisioned IOPS oftentimes for your disks that your database sit on, which is great. Provisioned IOPS are great, but you're pre-provisioning for those IOPS. With Aurora, you only pay by the IOs. There's nothing to pre-provision. So if you have a database, even a 64 terabyte database that's sitting out there, you will pay 10 cents per gigabyte, but then you don't pay anything for the IO requests unless you use it. In this particular scenario here, we're looking at about 93 gigabytes worth of data a month, and we're just ballparking, we'll say 2 billion IO requests, which honestly is probably a little bit on the high side. The total price out the door is about $644. So with that, I'd like to introduce Brian Philpott. Brian is the Director of Business Intelligence with Zillow, and he's going to tell you a little bit about their experience working with this.
Thank you, Steve. Can you guys hear me okay? Thank you. So Zillow, for those of you who don't know, we are the leading real estate and home-related information marketplace dedicated to empowering consumers with data, inspiration, knowledge around the place that you guys call home. So who am I? Brian Philpott, as I mentioned, Director of Business Intelligence at Zillow. I've been at Zillow just about 8 years come this December. Previous life, I spent around 6 years consulting throughout North America, Canada, Caribbean as well. So let's talk about the use case we had at Zillow. So somebody came to me and said, Brian, we have something that's shipping in 3 weeks. We need you to collect millions and millions of real-time data points. We're going to send it to a URL. I need you to create that URL. And again, the code's already written. It's shipping in 3 weeks. So you better get your act together. We have to aggregate this data throughout the day. And the business owners need data feedback. They need information on reports throughout the day. So, what did we do, right? I knew right away that it was going to be hard to set this up in-house, right? Procure servers, work with other teams, and get this up. We already run a large infrastructure in AWS. Our data warehouse is primarily run in AWS, so we knew we wanted to use Kinesis. So we happened to reach out to our solutions architect, who just so happens to be Steve. So after an hour conference call, we had our game plan in place. We knew what we wanted to do, which was, you guessed it, API gateway. We created a custom URL endpoint in Amazon Gateway. To start with, we're doing about 16 million posts a day. We send that data from the API gateway using Lambda functions. So we wrote a Lambda function that puts the data from the gateway into Kinesis. We then use another Lambda function to pull the data out of the Kinesis, and we encrypt that data using KMS, and we store it in S3. We analyze our data with Spark on EMR. We kind of run several Spark jobs throughout the day to run a whole bunch of analysis on this data, aggregations, and so forth. We also have the ability and the option to consume it in real time if we want, right? We're kind of doing more of a 4-hour batch processing at the moment, and that's just due to the nature of the data we're looking at. But if we ever need to get there, we have the ability to just analyze it kind of in real time. So here's just kind of a quick architecture diagram. I think Steve has been over this a bit. We have a mobile client. We're calling the API gateway. From there, we have 3 shards set up in Kinesis, and from there, we're going to our S3 bucket and then running Spark jobs. So what were some of the challenges and the problems that we ran into in developing this? I would say, we wrote our solution in Node.js. We've never really written anything in Node.js before, but it's not overly complicated. We had to figure out how do we concatenate lines and put a carriage return between them. Well, quick Google search, right? Solved it for us. The hard part with Lambda was it's just a relatively new product, and there's not a ton of documentation or Stack Overflow articles or blog posts. So we actually spent a bit of time trying to figure out how to read data from Kinesis, encrypt it with KMS, and then write it out to S3. That by far took us the most amount of time, and that was probably half a day at most. In all, it took us 2 weeks to develop this entire solution. That was with one developer, and honestly, that developer was probably spending about 50% of their time working on the solution. And it was actually 57 lines of code for us to do this. And that 57 lines of code includes error handling, creating references to KMS, S3, various Amazon services, error handling, et cetera. So in reality, it was probably about 10 lines of code for us to collect 16 million bits of information throughout the day, record it, store it in S3. So extremely quick, extremely fast, very, very little development time for us. So let's talk a little bit about the data collection costs. Using 3 Amazon Kinesis shards costs us about $1.30 a day, which includes our hourly put costs. Lambda, we allocated 128 MB for our memory. It runs about $6 a day, kind of depends on our traffic and what we have going on. So, I mean, you can see that this is just extremely cost effective, right? I think that's about the third of the price of what my dinner cost me last night. So very, very, very cheap, and just 2 weeks to development. I'd say the other great parts are, right now we're doing 16 million puts a day. When we want to go to 160 million or 500 million a day, all I have to do is reshard my Kinesis stream. No additional work. I don't have to patch servers. I don't have to allocate new hardware. I don't have to worry about load balancing. I'm done. That's it. That's all I have to do. So huge just time savings. Worked perfectly for us. So on the data analysis side, let me just talk about that for a minute. I mentioned that we use Spark to perform our ETL, data cleanup analysis. We run some ETL on this data. We convert it to Parquet. We do our data partitioning, store it in S3, et cetera. At Zillow, we run a ton of EMR. We run Presto, kind of for our long-term querying of the data. We also use Amazon Redshift. We use Amazon Redshift kind of for I'll call it our hot data, our most recent data that's very, very important to us. We tend to try to keep that to about a year. And then we store the rest of it on S3, and using S3 as our HDFS. And that's where you see Presto for your long-term queries, along with some people, data science doing Spark. As I mentioned, we're running about 4 jobs a day, using a data pipeline to launch our Spark jobs to kind of process this data that we're recording with Amazon Lambda, Kinesis, et cetera. So that's what we did over at Zillow. What else do we use? Well, we use Redshift. I mentioned that for fast access. We are huge users of Presto EMR. We also run Amazon SQS, data pipelines, SNS, S3, KMS. We want to encrypt our data, right? Our users' data is super sensitive. We don't want to leave it out there unencrypted. Gateway, we run EC2. Hopefully everybody heard the Firehose announcement. That's something that's not up here, but that is something that myself and my team is super excited about. Basically allows us to take the data right out of our Kinesis stream and just put it right into S3. So before I finish, just one kind of shout out to Zillow here. We are hiring. We are hiring ETL engineers, software developers. Certainly all open positions can be found at Zillow.com. More than happy. I'll stick around, answer any questions you have. You guys can also find me on LinkedIn. My last name is super unique. There's only one Brian Philpott in the world. You shouldn't have any problems finding me. Thank you, Steve.
Thank you, Brian. All right, so let's get on to what is normally everyone's favorite part of these presentations, which is a demo. Give me 1 second here. Okay. So, a lot of these things that we've talked about today, many of you are already very familiar with. S3, probably Kinesis, a lot of these things. Some of the things that maybe you're not as familiar with are Amazon API Gateway and Lambda. So we're going to spend the bulk of our time talking about this and looking at a real-world actual implementation of this. So what we're looking at here is the Amazon API Gateway console. From here, you can see you can just click here and create an API, but we're going to take a look at this API that I built for what we were talking about in the slides. So in here, we have our API. You can create resources off of that API with the Create Resource button right here. You can specify the path, and then you can attach methods off of those. In our particular API, we are simply using a post right off of the root. We're not going to create separate resources. Once I've created this post method, then I'll go into the method request, and I'm going to specify in here 3 different parameters. They're going to come in on the query string. You can also accept post data. You can accept however you need to pass the data, but in this particular scenario, we're just going to pass the data on the query string. So param 1, 2, and 3. Once we've specified that, we come over here to the integration request. We take the Lambda function here. The advanced just shows the AWS service proxy, but these are the 4 that we talked about earlier. Specify my region, the Lambda function that we're going to execute when we receive this, and then we're going to get into the mapping template. So the mapping template, we're going to specify here that for the content type JSON, this is how we're going to transform it. So you can see we just have a simple template here that takes the input parameters for param 1, 2, and 3, and then creates these. They show up as variables once they hit the Lambda function. So once this is all put into place, you can come back here. You can click test your method. Say A, B, and C. And so you can see right here that our status was, this is the request we sent in. Here's our status back. This is how long it took. In the particular Lambda function that we're using, I just have it echo back the payload that I've received. So you can see how it comes through as a JSON object with the parameters A, B, and C. You can see the response headers. And then here's a more detailed log of exactly what just happened. So you can see setting up the actual API endpoint is very simple. There's no provisioning of servers, and this will scale as much as I need it to. Once you've designed your entire API and you're ready to deploy it, you can click on Deploy API. You can select a deployment stage, and then, or create a new one, and then you can click Deploy. We've already deployed it, so I'm not going to deploy it right now, but it's already out there. And so then let's take a look at what happens once we receive that request. So I have 5 Lambda functions here that cover the entire project, and we're going to go through and talk about each of these. So the first one, the one that's connected to that function, or to that API gateway, is the data collection Lambda. In this one, they're all written in Node, so they all export handler. There's an event object and a context object. These are always passed into the Lambda functions. We're going to go ahead and specify our settings, US East, the Kinesis stream that we're going to write to. We're going to stringify this payload so that we can have a data object to pass through. And then you can see it's very straightforward. We're just calling it put record. And then we return Kinesis put failed or succeeded. Once it's in there, then we can take a look over here. Sure. I forgot how you zoom in Chrome. It's in the Control plus. All right. Is that better? All right, great. So in here you can get a glance at how your function is performing. And if you want to look in more detail, you can click on the CloudWatch logs. This will show you an actual breakdown of your console.log messages that you put out. It also tells you the memory size that you're using and the memory that you've used during the execution. And something else to note is the duration right here. So it took 69.55 milliseconds, but we're billing it out at 100 milliseconds because we do 100 millisecond increments. Okay. So let's go on. The larger font makes it a little difficult to see everything here, but it shows up for everybody back there. All right, the Kinesis reader function. This is what happens when we're reading from that Kinesis stream, right? So we've taken this function and attached it. So when records come in, we get a batch of those records. They come through in the event object as records. Note that the event and the context objects, they change depending on what they're attached to, whether it's a Kinesis stream or it's API gateway or how it's being used. We're going to for each through those. We're going to create this string. We'll use zlib, which ships natively with Lambda. Once it's zipped, we're going to put it into S3. It's the same sort of thing. So you can see these are very short, very simple functions. And a lot of your Lambda functions are going to be exactly that. Once it hits S3, we're just going to take and extract the bucket name and the key, and we're going to make sure that it's not a manifest file, because we don't want to put manifest files into SQS because they're not data files. We only want to put the data files that are in there. And then we push that into SQS, and then we return out of there. Now, these three are very simple, very straightforward. So what happens if you want to use something with, the Node package manager or something else? What if you want to connect to Aurora and you want to upload your data through Aurora, or to Aurora or Redshift? For those, it's a little bit more involved. So let's take a look first at the MySQL one. Still, it's fairly similar. I'm specifying a number of settings here. You can see that I've specified my encrypted password. I've encrypted this using KMS. And so I'm not storing any passwords in this Lambda function at all. We're going to time the execution of these things. So again, when that function is fired on Kinesis, we're going to for each through those. And instead of putting them together into a string that we're going to write into S3, we're going to take and create an insert statement. So insert into reinvent table, values, we append those here. And then we're going to decrypt the password using KMS. You can see, I'll show you what that looks like. You simply create a KMS client, you call decrypt, you pass in the ciphertext blob. Inside that ciphertext blob, it specifies which key to use. And assuming that the execution role that you have applied to your Lambda function has sufficient permissions, it will allow you to access that key and decrypt that key. I'm sorry, what's that? Nope, not necessarily, and I'll show you that too. I'll show you, you can look in RDS, and it'll show you, especially if you close those connections out, and we'll show you just how fast these things are getting put in there. So we'll go ahead and create the connection right here. We're going to execute the insert query, and then we're going to disconnect right here. Now, how do you deploy this? I mean, you have a folder that has the additional this MySQL library right here. So you can't really do that through the web console. So the other way you can do that is you can use the CLI to upload it. And so using the CLI, I just have a PowerShell script here. And you can also use the PowerShell tools as well, but I wrote this using the CLI so that it's a little more portable between platforms. But here we're going to take and zip up that entire folder structure. We're going to delete the function that's already out there. We'll call create on the function, and we'll pass that zip file directly up there that's got everything all packaged into it, including the MySQL library that you use to connect to Aurora. And then we're going to attach it to the Kinesis stream right here. So let's take a look at what this looks like once it's deployed. So the Aurora loader, you can look right here at the event sources. You can see that I've attached it to this reinvent Kinesis data stream. It's currently enabled, and it shows that the current status of it is OK. Click on monitoring like we did before. View the CloudWatch logs. And you can see right here as we go through, it shows the execution time for each of these things, 39 seconds, 98 milliseconds, et cetera. This right here is how you debug these functions, is by looking in these logs. Also, it's worth noting that when you deploy them, you can invoke them. If you call the invoke function, like we're doing right here, then once you've uploaded that function to Lambda, you can invoke it from your local workstation. In fact, if you happen to do this in Java and you use Eclipse, Eclipse actually has a plugin that will allow you to do all of this directly from within the confines of Eclipse. So let's take a look at what we did for Redshift. So for Redshift, we're going to use the Postgres library for loading data into there. And there are, and I'll just walk through each of these functions about how we did this. This first function right here is going to query SQS. It's going to pull the number of records that it needs, and it's going to, when it returns with the callback, it's going to pass the files, the list of files. The next one is going to create a manifest, which will just be a string in this particular case. The next function is going to take that manifest. Can you guys see this? Is this too small as well? Let me see, view, bottom left. Oh, yes. Is that better? Is that too big? All right. So maybe this will make more sense as I'm going through it. All right. So we want to get the list of files to process. So we're going to create a new SQS client and we're in the specified region, and we're going to loop, and we're going to go ahead and you can get messages out of SQS 10 at a time. So we're going to do a little bit of arithmetic to figure out how many executions we need to do. But the bottom line is that we're going to loop through, do 10 at a time, and then do the modulus at the end to get the last one to round it out. And that we're putting them into an array of ID and body. And we'll need those later on when we delete these records out of SQS. Once we have that list of files, then we'll loop through those and we'll create the manifest file. The manifest file, it really starts with entries and a bracket, then a bunch of URLs, and then ends with another bracket. We'll put that manifest into S3. It's 2 lines of code to do that. Again, decrypting the Redshift credentials. Now with Aurora, I just encrypted the password. With Redshift, there are 2 sets of credentials, and so I just went ahead and encrypted the entire copy command, and along with the credentials to log into the Redshift cluster directly. And so I put those into a JSON object. So we're going to create a KMS client right here. We'll specify the ciphertext blob. And then when it comes back, then we'll just parse it into an object from the plain text that was returned. And so now we'll see later on that we can use that for our authentication into Redshift. And then we call the load data into Redshift. And so we will connect to the Redshift cluster. Once we connect successfully, we'll call the copy command. So this credentials object is what we just decrypted using KMS. So you'll note there are no credentials stored in here anywhere except, well, actually, later on, I did leave them in the comments so I could show you what the copy command looks like. But again, we'll call done client.end to disconnect and then do our callback. Once we have committed those records to the database, then we need to delete them out of SQS. So earlier I was saying that we needed to make sure that we had the ID and receipt handle. So we're going to go through and we're going to pull those out, create the messages that we need to send back to SQS and say delete these so we don't reprocess them again, and then we'll delete those. And then the very last thing we do is we put our dummy record into the Kinesis stream that this Lambda function is running on. And so we just put the letter A using the partition key A into that Kinesis stream. And here, this is what the connection string looks like to connect to the Redshift cluster. So it's fairly straightforward, but this is part of what was encrypted. And the other thing that was encrypted is this copy command here, where we are specifying the table we're loading it to. We're saying we're going to load it directly from this S3 manifest file. The data that's in there is JSON encoded, so I've specified that it is JSON encoded and that we're going to use a JSON path document to specify how to decode that. These are the credentials that we're using, which are no longer useful. And then the time format, and then we're specifying that we're using a manifest and that it's been gzipped. And so what that all looks like without the commented sections below, which you would not put into your application, is this base64 encoded string, which is rather unremarkable. And then as far as executing these functions, we're just going through these and calling back and So let's take a look at what the output looks like in Redshift. So I think that's where we are. No, we'll go back to log groups. And we'll go to Redshift loader. And so you can see in here that we've requested 64 files from SQS because we want a multiple of the number of slices that we have on our cluster. We actually received 9, and we're going to go ahead and load them. If you wanted to optimize that, you would probably just use only, say, 8 if you have 2 or 4 slices. And then you can see the time that it took to create and put the manifest, 73 milliseconds, and then on and on. The rest of that's fairly unimportant. Now, once you have all of this set up, you want to know, how is this pipeline doing? How can I fine-tune this? Is this working, right? So we will click away from this. We'll go into here. So this is another new thing that was just released today, and this is the dashboards for CloudWatch. This is something I'm personally pretty excited about because it allows for you to create things like this. So if we're looking at these charts right here on this dashboard, along the left, what we have are the number of invocations of our API Gateway Lambda function. So you can see we're running pretty close to 40,000 invocations per minute. All of these are based on per minute aggregates. So we're taking in about 40,000 records a minute, pretty consistently. Then the reader function, the Kinesis reader function, you can see we're only executing about 180. Why is that? It's because we're processing that in batches. So your spend on AWS Lambda for processing those is practically nil. The Aurora loader, similar, and you would expect as much because it's feeding off the same data, 180 executions per minute. The S3 to SQS invocations, also similar. It looks like there was a small spike to around 210. And then the Redshift loader is a little bit slower because it takes longer to load all those data, all that data into Redshift. So we're looking at about 27 of those. And then along the right, you can see the duration, the average duration of each of the invocations. Now, where this is important is in a couple of ways. So one thing is you want to know, how well is this performing? You can see along the left, right up here, you can see how this was at 140 milliseconds. That was when I was playing around a little bit with the memory allocation that I was giving to that Lambda function. I believe that was running at 128 megabytes. And then I dialed it up to, I think, 512. And so you can see that the duration dropped dramatically. So it gives you even tighter control of getting that in there. The other thing that you want to consider is cost, because Lambda, obviously, you pay by the 100 millisecond slice. And so you want to try and find that balance between how much memory do I allocate and how many milliseconds is it taking to run. And OK, so that's where we are with the demo. We'll switch back. So just to recap, on the top left is what Zillow has in place right now. They have mobile clients writing to API Gateway. API Gateway uses Lambda to write into a Kinesis stream. Lambda functions on there that are feeding into S3, and then they're using EMR and Spark to read from there. We went over the Aurora one, which is very similar, except we're feeding data directly into Aurora. And then the third use case is also leveraging S3 SQS and the looping Lambda function to load data into Redshift. One other thing that I forgot to mention, as far as how real-time this is my Aurora instance right here. And note that the time down here is 2:23, if you can't see that. And when I execute this to look at the latest records, it looks like we just rolled over to 2:24. And the newest record in there was created at 2:24. So we are receiving these records from the point of ingestion to the point they show up in Aurora in about a second. So very real time. How about Redshift? Redshift's a data warehouse, right? Normally, the traditional thinking is that you need to run batch loads every hour, every 6 hours, something like that. Well, it's 2:24 still, and the latest record is 2:24 and 32 seconds. So we're still certainly less than a minute on that. There are a couple of other related sessions I encourage you guys to check out. Don't forget to fill out your evaluations. And then I'd like to take a few minutes here if anybody has any questions.